These are the notes for Unit 4, Day 2. These are on page 6 of your packet. And we're talking about contextual problems. So the focus for these notes are when we have contextual problems that involve motion. So this is going to be very physicsy. And so we are going to talk about straight line motion. So we're connecting position, velocity, and acceleration. We still have the same essential question: how am I going to decode these calculus problems? So the idea is being that critical reader and using those average strategies so that we can process what the question gives us and what the question is asking. So in the context of motion, then we're going to go through all of these definitions that you probably have done in physics. We're going to review them and we're going to apply those definitions to the problems. So motion along the line. So we consider this graph here of position versus time. And typically when you have a position function, we call it S of t. And so we have the position in miles, the time in hours. And so we are moving between the time intervals of A to B. And so for displacement from point A to point B, the displacement of an object over time is over the time interval delta t from A to B is its change in position, right? So we know that if we want displacement, we want this change in position. So how is the y-axis changing? So we call displacement then delta s. Delta represents change, s represents position. And so that is going to be the position at point B minus the position at point A. Change in any value is the final minus the initial value. So the position at point B would be this location up here. The position at point A would be this location here. Total distance traveled is making all the changes positive, all the deltas positive. So in other words, we are going to have to look, if we want total distance traveled, it's kind of like your odometer, right? If you start at home, drive to school, and then drive back home at the end of the day, your total distance traveled is twice the distance to school. And so we have to consider it, because like your odometer, it only measures positive distance. We have to find that turnaround point. For you, it's at school. We have to find that turnaround point and then consider the reverse trip as another positive distance, when we know that that reverse motion is really a negative displacement. So it's a little more involved. It requires us to find a turning around location. Okay, so the next term is average velocity. We see the word average. When you see average velocity, we've talked about this a few times already this year. We know velocity is a rate of change. So when we see the phrase average velocity, we have to think average rate of change. So it's the average rate of change of position with respect to time. So when we see average rate of change, we know that this is algebra slope. So here's the change in time, and here's the change in position. So the average rate of change of position, which is delta s, and with respect to time. So with respect to means divided by, with respect to time. So that is time b minus time a. So notice this is just algebra slope. We need 2 points to calculate algebra slope. So in the context of motion, we call it average velocity, even though it's just an average rate of change. And that was represented, since this is algebra slope, that's represented by the slope of the line connecting these 2 points. Remember, we call that a secant line, right? We started way at the beginning of the year talking about secant lines because we were touching the curve in 2 spots. It's not accurate as to what's happening, but it's a good average. Okay, so let's talk about instantaneous velocity now. So we see the word instantaneous, we know we're talking about the derivative. So the instantaneous rate of change of position with respect to time is the derivative. And so we know that instantaneous then is going to be the slope of the tangent line. And so if we talk about at point A, you notice this tangent line looks a lot flatter if I had to estimate a tangent line there, it looks a lot flatter than the average velocity. So at point A, we're going slower than the average. And so there is the velocity at one moment of time. There's the tangent line. It's flatter, so it's got a lower slope than the average velocity. But we can take a look at the instantaneous rate of change at several locations between A and B. Okay, so we'll do that in a second. So the instantaneous velocity at point A is the derivative of the position at point A. So we take the position function, we differentiate it, and we put in value A, and that is our instantaneous velocity. That will represent the slope of this line. The speedometer in your car does not measure average velocity, but it measures instantaneous velocity, right? So that speedometer is going to fluctuate depending upon how much you press on the gas, right? And so that is your instantaneous speed. Instantaneous velocity can be positive or negative depending upon what direction you're going. Instantaneous speed is always positive. So after we calculate this, if we want the speed, we're just going to take the absolute value of whatever answer we get above here. So we've talked about position, we've talked about velocity. Now let's talk about acceleration. We know that acceleration is another rate. It's a rate of change of velocity with respect to time. So it's looking at how our velocity is changing. Are we speeding up? Are we slowing down? That sort of thing. Do we have a positive rate of acceleration with a positive velocity? Then we're speeding up. If we have a positive rate of acceleration with a negative velocity, then we're slowing down. So it's looking at that, and we'll talk a little bit more about that also in a later note session. And so the acceleration is the rate that the velocity changes. So if you notice, let me replay that animation. We start with an instantaneous velocity at point A here, but as we go along this function, the tangent line gets more vertical. So we know that this is pretty flat at the beginning, it's pretty vertical at the end. So our rate of change in velocity is increasing. In other words, we're speeding up. That curve is getting more vertical. So we know the rate, the quickness or slowness with which the speedometer is the quickness or the slowness with which your speedometer in your car changes. And that's the acceleration, right? If your speedometer is going up really quickly, then you're accelerating at a great rate, so to speak. So that acceleration then at point A is going to be the derivative of my velocity evaluated at A. But if you remember, the velocity was already a different derivative of the position. So it's a second derivative of position at point A. So let's talk about putting ourselves in motion and what it means to move forward and backwards. So if the velocity is positive, we interpret that as moving forward. If the velocity is negative, we interpret that as moving backwards. If we're at rest, then we have zero velocity. Ironically, as we're turning around, we also have zero velocity, but we're also looking at either side of the velocity values and making sure that the velocity is going from positive to negative or negative to positive. Moving towards and moving away. So when we talk about relative to the origin, if we have a positive position, if we think about a number line, we're standing out in the positive numbers and we're moving in a positive direction, then we're moving away from zero. And if we start out in the negatives and we move in the negative direction, in other words, moving farther away from the origin, that's also moving away. So notice the signs are matching. Position and velocity signs match, means we're moving away. If the position and velocity signs are opposites, if we start in the positives and move towards the negative, then we're moving towards the origin. Or if we start in the negatives and move in the positive direction, again, we're moving towards the origin or towards zero. So how does that look graphically? Well, if this is velocity, this shows that we have negative velocity right here at this location. And so we must be moving backwards. We've got negative velocity. Here we've got a velocity of zero. So we must be at rest. And if you notice, on either side of this point, we go from negative to positive velocity. So our velocity is changing sign. So we also must be turning around. At this location, we're at positive velocity. So we must be moving forward. And we also have positive velocity here, so we're still moving forward. So that's how to interpret a velocity graph in terms of forward and backwards. Let's look at a position graph. So if we have this position here, we are at a positive position, S is positive. But look at our tangent line. Our tangent line is negative, which means our slope is negative, which means our derivative is negative. That's the velocity. So we have a positive position and a negative velocity. So we must be moving towards the origin. You can think of this as the origin, right? The horizontal axis. So we have a negative velocity. We must be moving backwards towards the origin. At this point, our tangent line is horizontal. So if our tangent line is horizontal, that means our derivative is 0. But if you notice on either side of this point, we go from a negative slope to a positive slope. So V changes signs because this is a position graph, right? So any slopes are velocities. So we must be turning around here. So we can literally think of this as going towards the axis and then away from the axis and turning around back towards the axis. And then we go away from the axis and turn around again. Okay, so it's at rest, we're turning around. Here we've got negative position and positive slope. So negative position and positive slope. We're moving back towards that origin. Okay, so since we have positive velocity, we're moving forward, back, and we're moving towards 0. And then here we have 0 velocity again. So we must be at rest. We're also turning around because we go from a positive slope to a negative slope. So that's how to answer those types of questions using your position graph. So when are we at rest but not turning around? So think about that. At rest, velocity equals 0, but not changing sign. Does that make sense? Okay, so we're at rest, but we're not changing sign. Let's talk about the total distance traveled. We can only do that on this position graph. Okay, because we have positive and negative positions. So we go from 3 to 0. So that distance is 3. The displacement being negative, but we want total distance. So we want all positive values. So this is 3. And then we travel from the origin out to 5. So 3 plus 5, and then back to the origin. So 3 plus 5 plus 5. I'm just reading right off the y-axis here. 3 plus 5, making them all positive, is 8, plus 5 is 13, plus 3 again is 16, plus another 3 is 19, and then plus a 1 here is 20. So my total distance traveled is 20. So that's how you can find the total distance on position graphs. Speeding up and slowing down is a two-step process, kind of like towards and away. We have to look at position and velocity. So speeding up and slowing down, we've got to look at velocity and acceleration. So if the velocity is positive and the acceleration is positive, we're speeding up. Same with if the velocity is negative and the acceleration is negative, we're also speeding up. Think about this as going in the positive direction and being pushed in the positive direction. So it's going to cause you to get faster. Same with going in the negative direction and being pushed in the negative direction. That's going to cause you to go faster. So when these signs match, we're speeding up. If the signs don't match, we're slowing down. So if we're going in the positive direction and getting pushed against us, that's going to slow us down. So that being the case, looking at the velocity graph, this becomes a situation of looking at the velocity values and the slope of the tangent lines, like we were doing on the previous page. So constant velocity means we're not doing either of these. So it must mean an acceleration of 0. So we're looking here, we have positive velocity. And if we look at the slope is also positive. So we have positive acceleration. So we must be speeding up. Here, we have positive velocity because we're up here in the first quadrant, but our tangent line has negative slope. So positive velocity, negative slope, we're slowing down. And here we have zero velocity because we're back at the origin. Our slope is negative. So we have negative acceleration. Our velocity is going from positive to negative. So our velocity is changing. So we know we're turning around here. And now we have negative velocity. And our slope is also negative. So we have negative acceleration. So negative velocity, negative acceleration. We're speeding up, moving away from the origin, basically. Okay, when would the velocity be constant? Well, the velocity is constant, oops, when the acceleration is zero. Where's the acceleration zero? Well, we'd have to look for a tangent line that's horizontal, which would be about maybe 2 seconds back up here. That would be a instantaneously constant velocity right there. Okay, so let's take a look at some work using this function and finding values, instantaneous values, using our calculus. So we have a particle moves along the x-axis, given a function x of t, which is right here. Gives the particle position at any time t greater than or equal to 0. So what's the particle's velocity at 3? So we know that from the context of this problem, because it's giving us a specific point, it's instantaneous. We know we need to use your calculus. So just a quick comment here. Notice there are no units given. So we don't have to put units on the answers, which is kind of weird. We're just looking for numeric answers. Okay, so here's our function. Let's differentiate that. So using the power rule, we get 6t squared minus 8t minus 8. And we want v of 3. So we're going to put 3 in there. And we're going to calculate that. So that looks to be, let's say 6 times 9 is 54, minus 24 is 30, minus 8 is 22. That makes sense. So that answer is 22. It's positive, so it tells us we're moving forward. At this point, if we had units, we'd put like meters per second on here, or whatever the units are. Okay, now it says what's the particle's acceleration at t equals 3. So we have our velocity function, so I've gone back to this expression. I'm going to differentiate that to get my acceleration. So that's going to be 12t minus 8. And I'm going to plug in 3. I need a of 3. So 12 times 3 is 36. Minus 8 is 28. So our acceleration is 28. If this was meters per second, this would be meters per second, or meters per second squared. Either one would be acceptable. At t equals 3, is the particle speeding up or slowing down, or neither? Okay, so it's asking you to look at your velocity value and your acceleration value. Your acceleration is positive. Your velocity is positive, so we must be speeding up. Okay, so that's how to navigate problems, computational problems using calculus. When we get into the classroom, then we'll go over the takeaways and from the notes and start our activity in class.